let's just consider what we might mean by the double integral over a surface of g of x, y, z ds. Now, we've already talked about surface areas. We now want to extend what we know about surface area and the way we integrate to get a surface area, and we want to extend that to be able to integrate a function over the surface of some region. Before we define what we mean by this, which is pretty much this, let's move over onto this side of the paper and consider the usual picture that the picture that we got when we talked about surface integrals. Okay? And the whole discussion comes down to what happens on the surface of some region in three-dimensional space corresponding to an area increment delta x by delta y down in the xy plane. Okay, so let's say that we have a surface z equals f of xy. I haven't sketched the surface. It'll go over a large region, and we don't want to complicate things by attempting to sketch the surface, but we got a surface defined by z equals f of xy, and that's something we're familiar with by this point. So, corresponding to this area increment down in the xy plane, we know that we get a rectangle up here on the surface, or an approximate rectangle. And we also know, and if you don't know this right off the top of your head, you're going to want to review it, that the area of this region up here on the surface, lying directly above or below this delta A area here, is going to be in the ratio, the area delta S will be in the ratio to delta A. Well, we're going to have delta A over delta S equal to the cosine of gamma. Now, clearly, the area down here in the plane is less than the area that you get when you project up onto a surface that makes some angle with the plane, so that the delta A is going to be less than the delta S, so that this ratio is going to be the cosine of gamma, where gamma is the angle between the normal vector to the surface and the vector perpendicular to the xy plane, that is the k vector. So that delta A over delta S equals cosine of gamma equals n dot k, where n is the unit normal. And I could label it as such up here, but let's not complicate the picture. So, it follows that delta S is going to be delta A divided by the cosine of gamma, which is delta A over n dot k. And this gives us the expression that we integrate to find surface area, the 1 plus fx squared plus fy squared times delta A. Now, I've thrown in an xi star, yj star here to indicate that, yes, we're going to look at a partition of a region in the plane, and this is going to be a typical partition, and we're going to have a sample point within that partition. Now, I should say that delta x is approximately equal to delta A over the cosine of gamma, because, of course, the result that we get here is going to depend on just where our sample point happens to fall within the region. In any case, using this, and we could say this could be a delta Sij equal to our delta A over the cosine of gamma, with everything evaluated at the sample point xi star, yj star. In any case, if we sum up all our delta Sij's, we get the area of the entire surface. So if we have, for example, a surface lying above a region in the plane, our delta x by delta y interval is going to be down here in the plane. Our delta S region will lie up here directly above that on the surface. The increment will have, the increment of surface area will equal this expression, this multiple of the area of our region down in the plane, and if we sum these up over all i's and j's, we approach this integral. Now, again, we've done that, and this is just a review of how we get our surface area. However, that's important. It's important to recall that and understand that so that we can understand what we mean by the integral of g of x, y, z ds. If we understand the idea of the surface area corresponding to an increment in the xy plane, then it's easy enough to understand what we mean by g of x, y, z times the surface area, the surface area increment. Okay, we have the delta x, delta y by delta x, or delta x by delta y region of the plane. We have a sample point within that region, which we call xi star, yj star. And above that sample point, we have a point on the surface. The point on the surface is what? Well, if the surface is z equals f of xy, then the point on the surface is xi star, yj star, z, where z is f of xi star, yj star. That is, z is f of xy, so that above xij star, yj star, the value of z is f of xi star, yj star. In terms of this integrand, it makes complete sense then that the contribution to this integral within this interval, or the contribution corresponding to this interval of our partition, should be the product of the value of the g function at this point multiplied by the area delta s ij, which means that we evaluate g at xi star, yj star, our sample point, and f evaluated at our sample point gives us the z coordinate. We plug the x, the y, the z obtained from our sample point into our g of x, y, z function, multiply that by the area, and that's our contribution to the integral of g of x, y, z over the surface. Now, as we showed here, delta Sij is equal to simply delta A, our area increment, multiplied by the square root of 1 plus fx squared plus fy squared, where fx and fy are evaluated at xi star, yj star, as it's written out here, so that the sum of our Sij, the double sum, the sum over I, sum over j, to get our total of all our Sij's, and that's not right, let me correct that. Okay, it doesn't look too pretty, but this should, we had the delta Sij here, and we should have had the g in front of that. So we're trying to sum up these contributions. So this sum of g of xi star, yj star, f of xi star, yj star, times delta Sij approaches the integral of g of xy, f of xy, times the square root of 1 plus fx squared plus fy squared dA. In other words, this just looks like our surface area integral if the g function isn't there, but the g function is there for the reasons we've outlined here. And how do we perform this integral? Well, for example, we just describe r by inequalities in x and y with dA equal dy dx. Our limits in the integrals are determined by our inequalities in the usual fashion. In other words, there's nothing really new about describing regions. We simply describe the region of our xy plane and proceed to write down our integral.